So, Mom, what's the big surprise? Why are we sitting here like blind Lone Rangers?
Yeah. Why can I still hear you with this mask on?
That humorous prelude from the legendary Kelly Bundy of Married with Children isn't there just to be frivolous, it's there to prove a point. She's a dimwit, an attractive dimwit, but still a dimwit. She's confusing two modes of communication, two different things. They are both ways to take in information, but there's a gross mistake when she confuses the ability to hear with the ability to see. And in that context, I want to show you a source for this hysterical myth, especially in ham radio, that because the antenna is mismatched, then there's a mismatch at the transmitter and a tuner is necessary, and I found a source for it. It is loaded with extreme mistakes that are grossly contradicted by this master level textbook. Brown, Sharp, Hughes, and Post. These were the masters of these topics. In one of my other videos about electromagnetics, I explained the problems with trusting engineers with this topic. Engineers get little training in the wave propagation and operations of transmission lines and antennas as transmission lines. And back in the early days, 40s, 50s, 60s, 70s, 80s, and such, they didn't yet know what antennas were. This hasn't been known till after 2000. But I'm going to show you an author held up to be a world's expert who's expert in other areas, who has proclaimed himself and had been proclaimed by publishing by the military and IEEE to be a world's expert, who has made an extreme, gross, and inadmissible flaw in analysis. And I've been telling you, trying to analyze transmission lines and antennas by circuit principles is a disaster, and I'm going to show you why. But here's my source. I don't take sources from backbenchers or second stringers. I don't take my sources from EEs, Brown, Iowa State, Sharp, Xerox, Hughes, Oklahoma University, Post. These were the legendary names back in the day. And the problem here is the false reliance back in the day up to the 1980s, maybe a little bit later, where high-powered computing was not available or ungodly expensive and slow, where they couldn't do these extremely complex electromagnetic transmission line and antenna analysis like they did now. I showed you an example of the paperclip antenna. It took NASA a month and guessing with 80 computers in parallel to figure it out. They could not do this in the 1980s, which is the source of the papers I'm going to show you. The problem is, and I highly recommend you get this book and read it, it's extraordinary, that in the circuit world, we reckon V on the left, curly Q V, as the magnitude V times cos omega t plus theta. That equation means for a certain peak voltage in a signal, the instantaneous voltage as it changes is the cosine related to omega, which is 2 pi f, which invokes frequency. That's the radial velocity, related to time and phase. Same thing with the current. Fancy curly I is I cos omega t plus theta sub 2. V and I mag are the peak values of the two signals. The critical thing to notice is that these equations relate to components with fixed values. And these components are in voltage, current, and time. You see nothing in there about distance. A series LC circuit has no concept of distance in it. Conversely, transmission lines don't contain these concepts. They contain concepts of distance and time. And there's the radical difference in why the systems are not interchangeable. No matter how desperately An engineer who is not a master of the transmission line question, how desperate that engineer is to assume that so he can force complex sounding math on it by computer. And that's what's gone wrong with education since the days of this writing of books like this. They got hooked on using computers, and now everything's got to be for the purpose of some extremely complex math system so they can look like geniuses solving their complex systems of equations. They do it because that's what they do. The critical distinction with transmission lines is transmission line analysis presented as a portion of text may well represent your first association with distributed parameter systems. That is radically different and separate from conventional lumped constant circuit theory. Lumped constant is LC networks. I've done videos on that, how to calculate a T network. Lumped constant means an inductor is a reactance or impedance here, a capacitor is a reactance or impedance there. There are networks that invokes network theory, and the paper I'm going to show you relates to two-port passive linear networks. That's a matching network. That's just all that means. There is no direct relation between a distributed parameter and a lump constant. If circuit theory is to be applied, necessary to attack transmission line problem from a differential viewpoint. I've done that in my videos. I've explained how circuits are coupled in transmission lines by that first differential of length of that line, coupling this signal into that initial extremely infinitesimally small capacitance at the beginning of the line. Since the properties of inductance, capacitance, and conductance are so hopelessly distributed and intermingled that they are not individually recognizable. This is the wrong example for a transmission line. It does not exist. These are distributed elements, but they're distributed so small and so finely that they cannot be recognized as individual entities. This is the idea behind the radar absorbing material on the stealth craft. There are systems like this represented by that matrix of finely ground up powders suspended in paint and put on airplanes. But a transmission line is not an inductor and a capacitor, an inductor and a capacitor. Because there's no way for that to represent a transmission line with an extremely wide bandwidth. Viewing the transmission line in terms of conventional circuit elements like the paper I'm going to show you, even though we derive the equations on a differential basis, differential equations, is very attractive, but at the same time rather naive. The individual transmission line parameters are computed on the assumption that the other quantities do not exist, and that is wrong, because they do exist. He goes on to say, fortunately, the results will be quite accurate. That's unfortunate because the engineers have taken that as being accurate, and it leads to an absolute disaster that I'm going to show you in this supposed expert's paper. And his paper violates the laws of physics. It's not just a question of which one is more proper. He makes a statement that contradicts laws of physics, and that is not admissible in science. Here's a representation of a differential length of a transmission line. See the dx? That dx means the length of that line is so close to zero that it's only an atom wide. It isn't real. As the length of those wires goes to zero, there's no inductance because inductance is about length. We can look at the ends of the wires, and until it vanishes, we can see a plane and dielectric and imagine some capacitance. So the line is approximately only capacitive. And that agrees with the losses being in a dielectric, and that's predominantly capacitive. But that's the only circuit construct that applies to transmission lines, is that capacitive line loss. Here are the circuit equivalent equations for a lossless transmission line. We see in these differential equations for a circuit representation of a transmission line, we see upper left V over X. We see I at the upper right over T. We see L, and of critical importance, that capital L means a constant value of L. Bottom Upper left, I over X. Right, V over T. C is a constant. These are the differential equations to calculate voltage with a signal changing over an inductor in time. V equals L di dt is exactly what's on top right. And I equals C dV dt at the bottom right. This is just a statement of the fundamental equations for inductors and capacitors. They come up with a pair of equations, LC as a function of V over time squared, and LC as a function of I over time squared. Moving right along, we see X, Y, T, and V. Voltage? No. Look at that V very carefully. That V is not that V. Classical wave equation. Y differential with respect to Y over X. On one side, Y over T on the other side, and 1 over V squared, which is velocity. Notice in that wave equation, there is no such thing as voltage, current, resistance, or impedance, and this is the transmission line problem. And this is where the computers throw up, because this is traveling at much of the speed of light, complex waves that can take many different forms in 3 dimensions, and they had no hope of calculating that by computer decades ago. It's a problem now. It's a supercomputer problem, and they couldn't do it. Further, this is a form associated with propagation down transmission line. Y, which is Y position. See the graphs with the wave travel. See the delta x equals 4 delta t and that increment of distance. This is a representation of a wave function, and it contains these parenthesis terms t minus x over v, and what that's referring to is velocity is position divided by time. So this is entirely in the time domain, and this is why we have to use time domain reflectometry to correctly test and understand transmission lines and antennas. But see, that went from this 2-dimensional, this can be represented in 2 dimensions, to a nasty 3-dimensional problem. Now the author goes to this wave function related to voltage, puts in with the position function in 2-9, includes voltage, current, and resistance in a position function, and comes up with the equation that people that believe transmission lines or circuits hang their hat on. R sub naught equals square root of LC. Notice, master level text, not an engineer who's a specialist in other fields and thinks he's an expert in antennas, but the masters. Do you see Z in there anywhere? You do not. A transmission line has the velocity V is found by comparison of equations 2.7 and 2.5. The characteristic resistance R sub naught is related to the square root of L over C. But understand, the line is not lumped inductance and is not lumped capacitance, and that's what those capital L and capital C mean. Constant values. For a line 10 feet long, there will be a value of L and a value of C. And critical point to remember, that does not change and cannot change. Hold that thought. The voltage to current ratio in each of the traveling waves is exactly the characteristic resistance of the line. Resistance, or a resistive system, has no idea what frequency is. Resistance is a chemical property. The copper wire conducts current because of chemistry. Resistance has no regard for frequency, so it is not impedance. Critical statement, very important that the waves traveling in both directions on a line be viewed as evidence of precisely the same phenomena and with each obeying precisely the same mathematical rules. The transmission line is bidirectional and reciprocal. Concentric transmission line at the top, R50 in, R50 out, and never anything else. The huge screaming contradiction I'm going to show you is that the same person or people that demand that this transmission line is somehow changed because it's mismatched, which means the transmission line has somehow changed its characteristic, are also the same people that hang their hat on this square root of LC, which is fixed and cannot change. And it is an infinite contradiction, and they are wrong. We cannot have incorrect things going into science because we get garbage in, garbage out. A T-network can have an R in and an R out of different values. Now that network can be turned around backwards. It makes no difference which is input and which is output because it's symmetrical each side of the inductor. But if R in is 50 and R out is 75, then you've got the networks. I have out networks, but networks on my antennas to match a 50 ohm transmitter to the 75 ohm line. That network can be turned around any direction you want as long as the input of 50 looks out to the left to something that's 50, and R sub out on the right side, which is 75, is always looking out to something at 75. And that's what matching networks at the feed point are all about. Now going on, important question. What load resistance, not impedance, resistance, may be used to terminate a finite length transmission line without reflection? And this is the definition of a matched line. It's important to note that there's no such thing as a mismatched line. The people that hang their hat on the square root of L over C, which is 50, that line is always 50 regardless. Nothing can change it because that value is also known as a log ratio of the mechanical dimensions of the line, and those are constant and never change. The terminating resistance value, not impedance, is exactly the characteristic resistance of a line R sub naught, since the voltage current ratio everywhere along the line is R sub naught for a case of an infinite line. This situation will not be disturbed if the line is cut at any point and terminated in resistance R sub naught. Nothing changes the line. But these fantasies of a mismatched antenna changing the line are what's desperately wrong with the electrical engineers trying to make this about electrical circuits. It isn't. Okay, here's the most critical part of the problem. Example. 50 ohm source on the left, 50 ohm line, R sub L, 50 volt pulse instant on a 30 ohm load. 50 on the left, 30 on the right, big mismatch. The incident wave from the source is independent of the line length and load resistance. Did you catch that? The load resistance makes no change on the mismatch. Load resistance on the right has nothing to do with the match on the left. That proves that what's in between is not a lump constant network. If it were, that would be the case. Incident wave from the source is independent of the line length, in other words, not concerning losses, and the load resistance. And is found by simple divider, voltage current divider, analysis between the generator internal resistance and the characteristic resistance of the line. So it's assumed that R sub G, with an ideal source, R sub G is 50. So the load has no effect on the source. Critical. Signal travels to the load with velocity v and is reflected because there's a mismatch. The reflected signal is computed from the application, yada, yada. The reflected signal travels back toward the generator and is reflected there by the mismatched resistance levels in the same fashion as at the load. Here's where the idea of a mismatch at the load on the left creates a mismatch at the source on the right and is reflected on the left. Or in the transmitter analogy, it goes back to the transmitter and is reflected again. And as the myth goes, it's eventually radiated. No, if that's happening, it's eventually eaten up by the losses in the line because the losses are bad. This text says, and notice, electrical circuit analysis being applied to transmission lines. Red lights start going off. Reflected signal travels back toward the generator and is reflected there by the mismatch resistance levels. In the same fashion at the load. Houston, we got a problem. I just showed you that the same source said that with the incident wave, the nature of the load made no difference and that the line is reciprocal. What's the problem here? The problem is not that the line is mismatched. And this is where the matching network fallacy comes in. They say there's reflected power back to transmitter. There's a mismatch. We got to put a network in or tuner and match it. There is no mismatch at the source. The source hasn't changed, R sub G hasn't changed, and the characteristic of the line has not changed. What happened is that a voltage and current were reflected, and they come back and they add with the instantaneous voltage and current to the right of R sub G. And this changes voltage and current levels. It has nothing to do with the circuit or the line. And understand, here's the source of this false applying this circuit analogy to the line. And the paper I'm about to show you takes this block by the distance arrows D, characteristic resistance R sub O, and treats that as a lumped constant network. And that's a gross mistake, because the mistake they end up making is to say that the improper R sub L, or the mismatched antenna, causes a mismatch at the receiver and changes the impedance of the receiver R sub G. That violates the laws of physics. It can't happen. But this is a disaster that comes when they start getting away from transmission line theory and start trying to play circuits with it. You ever operated a tube amplifier? Worked fine one day, next day there's ice on the antenna, you don't know it, you fire it up and the plates turn red. Don't tell me about energy coming back down the line and reflecting at the transmitter. Folks, I've seen that. It ain't reflected, it turns the plates red. Been there, done that. Been there, dive for the switch to turn the amplifier off. Here's where the fault gets propagated and becomes impossible to separate out. The mistake of considering a transmission line as a circuit element, and that's what the paper I'm going to show you does. Transmission line has properties in common with lumped constant circuit elements, but at the same time properties are very different. Transmission line can be used in combination to produce the equivalent series of parallel tuned circuit. In that sense, it's similar in behavior to lumped constant circuits. However, contrary to lumped circuit elements, the transmission line exhibits not one or several resonant frequencies, but an infinite number of resonant frequencies. Therefore, it is not a circuit. No circuit can have an infinite number of resonances. The text goes on to say that a line terminated in a reactance has the input end that looks like a reactance. This goes back to what I told you about a reactance causing reflected energy that's out of phase. Well, that arrives at the first end of the line, and that's the voltage and current that's out of phase. But again, it did nothing to the line. It did not change the line, and the line itself is not reactive. But here's a super important thing to notice if you're doing antenna graphs. Reactance, variation of lumped and distributed elements versus frequency. Graph on the left, shorted line. See the here? That's a shorted line. That's an inductor. There's an open line and a capacitor. These asymptotic behaviors are what show up on your antenna analyzer computer screen. when the frequency is away from the frequency that it's matched at. It's not resonant circuits. This is the behavior of the antenna as it approximates a shorted or open transmission line. And this goes to show my point. Antennas are not circuits, they're transmission lines. And they can't be analyzed by circuit principles because they aren't. Similarities between distributed constant and lump constant circuits, they warn that all frequency exact equivalent of a circuit for a section of transmission line can never be obtained with lump constant because we cannot with a finite number of elements generate a reactance that's a transcendental function of omega as required of all the elements in a circuit. Transmission lines are not impedance, they're resistance. Recall what I told you, resistance does not acknowledge omega, which is 2 pi f. Here's an oh my gosh, expert, lasers, antennas, and tigers, oh my. Honeywell, Fluxgate, gamma ray, spark, X-ray telescopes, cathode ray tubes. Formal employment in things, high altitude nuclear explosions, formal employment with big corporations that are not antenna related. And then claims of other vaguely electromagnetic, physical, electronics, optics, lasers, and antennas. Houston, we got a problem. This individual might have been extremely highly educated, but in the paper I'm about to show you, there's a extremely gross error. Paper titled Noise Factor of Receiving System with Arbitrary Antenna Impedance. This assumes a grossly mismatched antenna because it's too small, and studying the noise effects. Noise factor of receiving system is antenna's impedance matched to the transmission lines feeding the receiver. Antenna external noise at frequencies below 100 megahertz. Large impedance mismatch noise factors for the line and receiver can be significantly increased. Notice that's not a very remarkable statement. When we go down here, noise factor of the transmission line increases with increasing mismatch source impedance, that's the antenna of the line, to its characteristic impedance. Wrong. Lines do not have impedance. And this is characteristic impedance because he's about to treat transmission lines as lump circuits, and it isn't. Because of decreased available signal power to output of the line, which is at the receiver. Of course, if there's a mismatch, there's going to be a lack of energy transfer to the receiver. Here goes the problem. Noise factor of the receiver as in any linear two-port network. So the receiver is a two-port electrical network. It is. But this can't be processed to include the transmission line unless he artificially invokes the transmission line as a two-port linear network, and it isn't. Here's where the disaster comes in. Thus, a large impedance, nope, there's no impedance. There is at the matching network that he has put there because the antenna is hopelessly screwed up. That network will have an output impedance. Oh no, wait a minute. Networks can't have an impedance on their input and output. They got to be resistive, and I proved that from another expert, Terman, Radio Engineer's Handbook. A large impedance mismatch at the antenna transmission line interface up there at the antenna. Here's the screaming problem. May cause the source impedance of the receiver to be substantially different from 50 ohms and consequently may cause an appreciable increased noise factor for the receiver. That is false. Nothing of an antenna mismatch. This was stated by the engineers at Radio Magazine in 1936. No mismatch at the antenna is going to change the receiver in any way. Did a mismatch at the antenna change the position of a slug in a transformer inside the receiver, or did it change the value of a capacitor? Did that mismatch magically stretch the size of the shield on the coax where it connects to the receiver? If you think it did, check yourself into a mental institution, because it didn't. The point of this paper is a model to show that when the antenna is mismatched, that the signal and the noise from the antenna toward the receiver go down. Well, there's a mismatch. Any energy picked up by the antenna that goes to a mismatch is some of it's going to be reflected. It's not going to be an efficient transfer. But in that case, it is known that the noise as a result of that mismatch can go through the roof. And this paper is trying to explain why that happens. And that noise cannot skyrocket because of an antenna mismatch, because the antenna is not the source of the noise. Here's another paper on a similar topic about signal to noise ratio, a little bit different part of the topic, 1985, published by the government, the military. Ooh, it must be right. The military published it. Yeah, NASA managers killed a bunch of people because they thought they were right too. And here comes the problem again. The premise of these papers is that when there's a mismatch, the extreme increase in noise is caused by a mismatch at the antenna that causes a mismatch at the receiver, and the increase in noise is due to noise factor or figure in the receiver. Never mind, what caused this in the first place was a mismatch at the antenna that reduced the amount of noise coming from the antenna. It's an extreme contradiction. And this is his founding claim in both these papers. When there is a large impedance mismatch at the antenna transmission line interface, pre-detection signal noise ratio can be reduced because of decreased available signal power to input to the receiver and increased noise factor of the receiver. Yes, the antenna is the source. There's less signal and noise coming down the line, so the receiver has less to work with. But then magically, somehow this mismatch causes the receiver to generate more noise. And he's citing a figure of upwards of 50 dB. How can an antenna, being a source, which is now not transferring signal or noise energy to the receiver, cause a 50 dB increase in noise at the receiver? And the same false assertion repeated. That this is his catchphrase. Large impedance mismatch at the antenna transmission line interface may cause receiver source impedance to be substantially different. That appears to be the case from our expert book I just showed you. To be substantially different from 50 ohms, consequently may cause an appreciably increased noise factor of the receiver. Noise factor, not noise, because the noise went down. This false reliance on circuit equivalence of a transmission line that leads to this fantasy. He has claimed, I don't see where it is, but he's claimed a 50 dB increase in noise with a mismatched antenna. Put the wrong resistor value on your receiver antenna input. Do you suddenly see an S meter jump up to 50 dB? You do not. Take your matched antenna, change frequency of the receiver to where it's not quite so well matched. What do you hear? You hear the signal and noise going down. There's something else happening here, and I've found it. And it can only be understood by abandoning this principle of the line as a circuit. I can't tell you what it is because I'm writing a paper on it. I've had to find this for a source of what has been previously published on this topic, but what's published here is gross error. And it gets lost in a noise of piling on piles and piles of mathematics, which are mathematica obscura. They hide what's really going on here, and it can't be seen. Cannot be seen by treating the transmission line as a component network. It does not work. Conclusion, large impedance mismatch at the antenna transmission line interface, blah, blah, blah. Significant increase in system internal noise factor, more than 50 dB. I've measured that too for a voltage reflection coefficient of 0.99, which is an extreme mismatch at the antenna. It is not because of the receiver, it's something else, and I found what it is. And here's a statement that apparently contradicts the previous. Antenna impedance mismatch significantly affects the transmission line noise figure. Noise figure is not noise. Noise figure, signal to noise ratio are proportions. How much signal there was before the noise went up. and to a lesser extent the receiver noise figure. Well, no, wait a minute. The entire point of the paper is that the receiver noise figure is a problem. The system operating noise figure is not significantly affected by mismatch until the voltage reflection coefficient, gamma of R, is about 0.98, which is essentially an open-ended line. Something happens there that he did not catch. And he could not catch it assuming that this is circuits. It's impossible. But by considering what a transmission line really is, I found it. And it's fascinating. But I can't tell you what it is until it publishes. This video has broken the half-hour mark. I need to stop it and start another one because there's another 15 or 20 minutes here. But next, I'm going to show you the nature of this fallacy that reflected energy changes the impedance of a circuit. That violates the most basic principles of electrical science. But I'll continue this on the next video.